All right, hi everyone. This is worksheet 15.1, separation of U internal energy into components. Make sure you put your name there at the top right-hand corner. To begin with, I'd like to remind you of what we talked about, hopefully in lecture, that the internal energy is equal to the derivative of the log of the system partition function with respect to beta, keeping the volume constant. And if you use the definition of the system partition function from an ideal gas, this becomes n times the derivative of the log of the molecular partition function with respect to beta, which is equal to the negative n of the derivative of the log of the different Q's for the molecular partition function, so Q translation, Q rotation, Q vibration, Q electronic, with respect to beta. And remember that beta is equal to 1 over kBt. It's just sort of a convenient shorthand for that expression. Okay? And we've still got constant volume in both of these cases here. Now, what does this equal ultimately once we spread out that logarithm? Well, it equals negative n times the derivative of log Q trans with respect to beta. And we're using the rules of logland here. Derivative of log Q rotation with respect to beta, plus the derivative of Q vibration with respect to beta, plus the derivative of log Q electronic with respect to beta. Hopefully you see how that follows there. Now notice what I can do now is look at the form of U right up here and see that since U is proportional to n times the derivative of log Q, little q, then you see how that pattern is kind of repeated for each one of these little sections here. That means that it's possible to break down U into a translational part, plus a rotational part, plus a vibrational part, plus an electronic part, at least for an ideal gas. All right, and we're going to look at each one of these expressions for the internal energy one by one. All right, so let's begin with U translation, which, as I pointed out, was the negative n times the derivative of log Q trans with respect to beta. And now I can use the chain rule to rewrite this as negative n divided by Q trans times the derivative of Q trans with respect to beta. And that follows, again, because of the chain rule. I get the derivative of the logarithm first, which is going to be 1 over the thing inside the log, times the derivative inside the log itself. Hopefully you believe me when I tell you that. Okay, remember that I told you that Q translation is equal to the volume of the system divided by the de Broglie wavelength cubed, which I told you was equal to 2 pi mkt divided by h squared to the 3/2 v. But I'm going to recast the de Broglie wavelength in terms of beta instead of kt. And so this just becomes 2 pi m divided by beta h squared to the 3/2 v, like that. And that's going to be a lot more convenient now to get the derivatives. Okay, so I'm going to start by getting the derivative of Q trans with respect to beta. And that's going to, if I take this expression here and get the derivative with respect to beta, I can just rewrite that as the derivative with respect to beta of 2 pi m divided by h squared to the 3 halves times v times beta to the negative 3 halves. Hopefully you agree with me there. And that just equals 2 pi m over h squared to the 3 halves v times negative 3 halves, and then I've got beta to the negative 5 halves because I took this exponent there and I dropped it down in front, and that's how I get that expression. This is a negative here, that's a multiply times. All right, and now when I put this back into this expression here, I get negative n times h squared over 2 pi m beta up there to the 3 halves, turning that upside down, 1 over v, and then I multiply that times my expression for the derivative, and I get 2 pi m over h squared to the 3 halves. Notice that that's going to cause these things to cancel out here. And then I have negative 3 halves. I'm missing a v, and that's going to cancel out with that v right there, so that's convenient. And then I've got beta to the negative 5 halves. And that's going to cancel out with this beta and turn that into beta to the negative 1. And then this negative sign here is going to cancel out with that negative sign there. And I'm left with 3 halves n divided by beta, which according to our definition of beta is just 3 halves nkt. And that, ladies and gents, is our expression for the internal energy of translation for an ideal gas. Okay, now for this next part, we're going to do u of rotation, and we know from the expression above that this equals n times the derivative of log q rotation with respect to beta, which, just like the translational part above, equals negative u over q rotation times the derivative of q rotation with respect to beta. And what is q rotation? Well, from class you know that q rotation is equal to 1 over sigma, which is the molecular symmetry, beta hc times b, where b is the rotational constant. And let's start by getting the derivative of q rotation with respect to beta. This just equals negative 1 over sigma beta squared, because this expression over here really just equals 1 over sigma bhc times beta to the negative 1. So when I get that derivative, that negative 1 comes down in front, and then I just subtract 1 from the exponent. And so then I can put that exponent back down into the denominator, and I get that. And now when I calculate n over q rotation times the derivative of q rotation with respect to beta, this becomes n times sigma beta hc b times 1 over sigma beta squared hcb, and the hcb's cancel out and the sigmas actually also cancel out, and one of the betas cancel out, leaving just n over beta, which is just nkbt. All right, I told you that the vibrational molecular partition function is equal to 1 minus e raised to the power of negative beta hc nu tilde, raised to the negative 1 power. Now, if you want to go and get the derivative of log Q vibration with respect to beta, it's a pretty hard derivative, so I'm just going to give you the answer of what the internal energy of vibration equals. I'm just going to give you the answer, but if you really wanted to, you could go try to find the derivative yourself. It is possible. The answer turns out to be n times Planck's constant c nu tilde divided by e raised to the positive beta hc nu tilde minus 1. All right, and that's the vibrational internal energy. But if T is large, then beta is small, right? And that would imply that E raised to the power of negative beta hc mu tilde is going to be approximately equal to 1 minus beta hc mu tilde, like that. All right, and when I take this expression and plug it in right there, that implies that Q vibration is going to be equal to positive beta hc nu tilde to the negative 1 power, like that. And the derivative of Q vibration with respect to beta just becomes hc nu tilde to the negative 1th. There's a negative sign there, beta to the negative 2 power, like that. All right, so when I go to get my vibrational internal energy, it becomes negative n over Q vibration times that derivative with respect to beta, which is just going to equal negative n beta hc nu tilde times beta to the negative 2 over hc nu tilde. So those just cancel out. One of those betas cancel out, so that becomes beta to the negative 1, and there's a negative sign there. The negatives cancel out. So once again, we're left with n over beta, which is just nkBT, for the high temperature approximation for the internal energy of vibration. All right, now the last section is the electronic one, and I told you that the electronic partition function is often just equal to the degeneracy of the lowest energy level. So this is degeneracy of lowest energy level, yeah. Then the derivative of Q electronic with respect to beta is 0, because the degeneracy is completely independent of temperature. So therefore, the electronic internal energy is just equal to 0. All right, so now we've got to add them all together. U is going to be equal to the translational energy plus the rotational energy plus the vibrational energy plus the electronic energy. This equals 3/2 nkt plus nkt from the rotation. This one was from the translation, this one was from the rotation, plus n hc nu tilde divided by e raised to the beta hc nu tilde minus 1, like that. And that's the total internal energy of all the different degrees of freedom. So now let's talk about heat capacities. You know that the constant volume heat capacity is equal to the derivative of the internal energy with respect to temperature at constant volume. And another way to write this, it turns out, though it's a little bit tricky to get this expression, this is going to be equal to kBT beta squared, the derivative of U with respect to beta at constant V. And if the translational energy is equal to 3/2 nkt, then hopefully you can see that the heat capacity of the constant volume heat capacity of the translational degrees of freedom is just 3/2 nk, because the derivative of T just goes to 1. And by the same token, the internal energy of the rotational state is just nkt for this linear molecule. So CV of rotation just equals nk. And the vibrational one is a little bit trickier, so I'm just going to write out what the answer is, but the heat capacity of the vibrational degree of freedom is a long one. It's nkb beta squared hc nu tilde, all of these are squared, over e raised to the positive beta hc nu tilde minus 1 times e raised to the beta hc nu tilde, and that's it. That's the vibrational heat capacity. I did that one by hand. I did all the calculus for that one by hand, so if you're feeling like you're ready for some pain, you can give it a try yourself, but I imagine that nobody will actually want to do that, so I have it listed out here for you.